Okay, let's see what this tells us, that Ki dot R equals Kr dot R. So we've decided that this happens when you have a dielectric interface at N and you have your incident K vector, Ki, comes in at some angle to the normal, theta I, and you have a reflected wave at wave vector Kr, and it is at an angle theta R. So we've decided that they're coplanar, but let's see what we could learn beyond that. If we know that K dot R equals K dot R, let's also, since we're working in the interface, let's put the origin here and just say R is this vector. So I'm showing you for this specific R, but this is actually true no matter how you define R. Okay? So K
His story could go anywhere, and that's what
one way to write it is just the magnitudes times the cosine of the angle between them. So we could say this is the magnitude of Ki times the magnitude of R times the cosine, and the angle between them actually isn't theta I. You have to put this tail to tail with that. It's actually 90 minus theta I. So that's that dot product, Ki dot R. And then we could do the other side, the magnitude of Kr and the magnitude of R, and the cosine of the angle between those. If we put this tail to tail with this, that's the angle, but the whole thing is 90. So again, it's 90 minus theta R. So if you look at that, a lot of stuff cancels. R, the magnitude of the R vector, cancels. Ki and Kr actually cancel because they are plane waves in the same medium. So they have the same wavelength. Right? They are 2 pi over lambda. Well, if the plane wave exists in the same medium and it's oscillating at the same frequency everywhere, if the omegas are the same, it has to be the same wavelength. So you can actually cancel Ki and Kr. Or you could write it as 2 pi over lambda I, 2 pi over lambda R, and you could still cancel it. So what we end up with is that cosine of 90 minus theta I equals the cosine of 90 minus theta R, which just means that theta I equals theta R. This is the law of reflection. The angle of reflection equals the angle of incidence. So we can show you this with a dielectric. So here is my little piece of plate glass, and I'm going to set it here. And here is my plane wave at 532 nanometer wavelength. And we're going to bounce it, but you need to be able to see it, right? You can't see a plane wave. I turned it on, you don't see anything except the dot where it hits the wall. So to see it, we'll get a little bit of smoke going by pouring liquid nitrogen in this little container. It's got some water in it. And here in Houston in the summer, we get very good smoke from liquid nitrogen. It's a little hot and humid here. Okay, so now what I'm going to do is bring this down, and there you can see the beam coming in and the beam reflecting up. And if you imagine a surface normal, you can see that they're at the same angle, the angle of incidence, the angle of reflection. And if I bring it down at a steeper angle, they both move by about the same amount. Again, you can imagine a surface normal, and the angle of incidence equals the angle of reflection. And if I bring it really sharp, they still stay together. Right? So you can definitely see the effect there. And bonus points for anyone who can tell right now why there's two beams coming out on the reflected beam. We'll definitely talk about it later. Maybe you already know. So now let's do it for the plane wave that is transmitted into the dielectric medium. We're going to do it a little bit different. I'm going to draw the interface, and instead of air being at n equals 1 and something like glass being in, like 1.5, let's be more general and say here this is some dielectric N1 and this is some dielectric N2. So really for any interface. That'll give us the more familiar version of the law we're working towards. So we know you have a vector coming in, K incident, and we know it's at an angle with respect to the normal theta I, or theta 1. We'll call it theta 1 since that's medium 1, and we'll call this K1 actually. And we know it's going to go in like that, and this will be K2 in the second medium at some other angle theta 2, like that. So we're going to use the exact same idea, the fact that K1 dot R equals K2 dot R. In this case, though, we're talking about a transmission into a different medium, not a reflection. And we're also going to do it for the case that the origin is somewhere around here, and we're just thinking of this R right there. Okay, so we just look at the magnitudes again. The magnitude of K1 times the magnitude of R times the cosine of exactly the same. You bring this R here, it's the cosine of 90 minus theta 1 equals the magnitude of K2 times the magnitude of R, and also the cosine of 90 minus theta 2. And I've not left myself room here. Cosine of 90 minus theta 2. I did leave room. What do you know? Okay, so now we look at what can we do to simplify this. Well, we can cancel the magnitude of R like that. That's the same on both sides. But we can't cancel K1 and K2. Before, when we did a reflection, they're in the same medium. Whether we called it N1 and N2, whatever you call it, they're in the same medium, so they have the same wavelength. Here, different media, right? So the frequency is the same, but spatially they're different. We know that K1 would turn into, let's see, it's 2 pi over lambda naught, the vacuum wavelength, times N1. And cosine of 90 minus theta 1 is the same as sine of theta 1. And then this one would be 2 pi over the vacuum wavelength times N2 times the sine, because cosine of 90 minus theta 2 is the sine of theta 2. Now we have more stuff we can cancel. The 2 pi's we can cancel, lambda naught to the same. And now we have N1 sine theta 1 equals N2 sine theta 2. And this is Snell's law. Also called the law of refraction. Just like this is the law of reflection, this is the law of refraction, or the law that tells you what happens to the angle when you cross into a denser medium. It describes this situation. You can kind of think of it, one way to make it easy to remember is that a plane wave falls towards the normal when it goes into a heavier medium. So you can kind of have a gravitational analogy. It's falling towards the normal at a heavier medium, because if you go to a higher N2, if that number is bigger, the sign has to become smaller to make this thing be equal, right? So that's why a bigger N means a smaller angle. And we can show you that this will happen here. So here I have a boundary between two dielectric media. I have air here, n equals 1, and I have water here, which is about n equals about 1.33. So I have my 532 vacuum wavelength nanometer plane wave here, and I can send it into the glass, but you can't see it in the air. So we'll use our Houston humidity again with some liquid nitrogen and get a little smoke layer, just enough to get some smoke, and that's a little too much. And I think you'll be able to see, once the dust settles here, the nice bend as the laser beam falls towards the normal, as it goes from the, there we go, as it goes from the air above, where you're just seeing the scattering off the condensation, to the water, where you're seeing scattering because I put something in the water to make it scatter. So there you can see the sharp bend of the beam as it goes into the denser medium in the water. It's falling towards the normal because the water has a higher index. So that's what we can learn about these angles. Now let's look at the amplitudes.